Well, hello everybody. We're going to talk about, we're discussing the broad topic of ray optics, and in this video we're going to focus on reflection. So, the propagation of light when diffraction or interference is not important. Remember that diffraction and interference is the phenomenon that we discussed in previous videos. So when those effects are not important, the propagation of light is actually quite easy. Light propagates in straight lines. So if you have a source of light at some location, a small source of light, like a light bulb or something like that, we can think of the light waves propagating outwards. And if we follow a small section of a wavefront, we notice that wavefront, the small section of the wavefront, is going to propagate in a straight line, as indicated by these arrows. So instead of drawing all the wavefronts produced by light, when diffraction and interference are not important, we just draw the direction in which a wavefront would propagate, and the different sections of a wavefront will propagate in different directions. So we draw these arrows that we refer to as light rays. So things are simple until light interacts with matter. So light is an electromagnetic wave, and it interacts very strongly with atoms and molecules. So when light encounters matter, then several things can happen. We can have reflection, we can have absorption, or we can have transmission. So let's start with reflection. Let's say that a light ray hits the surface of an object. So reflection means that the surface of the object is going to bounce back that light. The light is going to propagate is going to interact with the surface of the object, and the object is going to bounce back the light. But it can also happen that some of that light is absorbed by the molecules or the atoms on the surface of the object. So some of these molecules and atoms are going to suck in the energy from the light, and they're not going to give it back. So some of the light will get absorbed on the surface. But if we're dealing with a transparent material like glass, plastic, etc., some of the light would also be transmitted. It goes through the material if the material is transparent. So let's take a detailed look at reflection. So in reflection, we have two kinds of reflection. We classify reflection in two categories. Specular reflection is the kind of reflection that happens when the irregularities on the surface of the object are smaller than the wavelength of the incident light. So what does that mean? So we have light hitting a surface, and we're going to say that this surface, we're going to look at the case when this surface, the irregularities on the surface of the object are small. So how do we measure that? So we indicate here with h the distance or the difference in height between the highest point on the surface and the lowest point on the surface. So if the surface is polished, if it's very smooth surface, and by small irregularities we mean that the size of the irregularities is less or equal to the wavelength of the light that you're shining on the surface. So if that is the case, we say that the surface is smooth. And for a smooth surface, what happens is that an incident light ray is going to be reflected in a very predictable way. We're going to say that in the next slide, that the angle of incidence equals the angle of reflection. It's a very simple, predictable way in which the light ray is going to be reflected. And a light ray that is parallel to the previous one will reflect in the same way. So it's easy to predict in what direction the light rays are going to be bounced off the surface when the surface is smooth. So we call this specular reflection. The word specular comes from a Latin word that means like a mirror. The other kind of reflection is called diffuse reflection. So this is the kind of reflection that happens when the irregularities are bigger than the wavelength of the incident light. So what does that mean? So let's say that we have two light rays that are parallel to each other. They hit a surface, and it turns out that this surface is not very smooth. It has a lot of peaks and valleys, very irregular. And the size of the irregularities, h, is bigger than the wavelength of the light that we're using. So h bigger than wavelength, than lambda. So if we look at what's going to happen to the top light ray, Well, that one is going to hit this pointy part of the surface, and it's going to be reflected that way because locally, at the point where it hit, the surface had a slope like this. But a different light ray will hit a different part of the surface, which will have a different angle, and it will be bounced in a completely different direction. So in diffuse reflection, because the surface is so regular, it is impossible to predict in which direction the light rays are going to be. Any individual light ray is going to bounce off the surface. So this is the case. This is the kind of reflection that you have of the surface, of any surface that is not shiny. Any object that is not shiny, if you look around, all of these objects are reflecting light in a diffuse way. Now, specular reflection, as we said, has a very simple and nice property, which is that when a light ray hits the surface of what we're going to call a mirror, a flat mirror, so when a light ray hits the surface of a flat mirror or any shiny surface, then the light ray is going to bounce, and the angle of incidence is going to be equal to the angle of reflection. Notice that the angles are measured from a line that is perpendicular to the surface of the mirror. This is important to keep in mind for this chapter and the next chapter. So all these angles are measured from the perpendicular to the surface. So in 3 dimensions, when you have a mirror and you shine light on the mirror, the reflected light ray, it's going to be on the same plane as the incident light ray. On that plane, the angle of incidence and the angle of reflection are the same, but importantly, that plane in which contains the angle of incidence and the angle of reflection, or the light ray that is coming in and the light ray that is reflected, that plane is actually perpendicular to the surface of the mirror. So in 3 dimensions, this is how you would draw light rays being reflected from a mirror. Most of the time, we're just going to look at the 2-dimensional situation. Now, a very important thing that happens with flat mirrors is that they make images. So let's take a look at a green light bulb placed in front of a mirror. The light bulb is going to be emitting light rays in all directions. And we're going to start by looking at this light ray that was sent in this direction, and it interacted with a mirror. So the front of the mirror is there. The convention that we have in physics 2425 and 2426 is that this symbol means that the surface is smooth. So we have a shiny surface, otherwise known as a mirror, and the light ray, when it interacts with the mirror, we know that the angle of incidence and the angle of reflection are going to be the same. So the reflected light ray looks like that. And what we're drawing here is sort of tracing back the reflected light ray, and the reason why we're doing this will be explained in a minute. It's going to be very important. But let's take a look at another light ray. Before that, actually I forgot, this angle and this angle are the same, which is going to allow you, if you wanted to prove something interesting. But let me get that in a second. Let's take a look at a different light ray. So another light ray that hits the mirror at a different location. So again, the angle of incidence and the angle of reflection are the same. If we trace back that light ray, if we draw a line propagating behind the mirror, following the same direction of the reflected light ray, we notice that those 2 light rays, well, they're not light rays, the traced back lines are going to intersect at some point. The angle beta here is the same on both sides, just like alpha was the same on both sides, and this is going to be true for any light ray that hits the surface of the mirror. And using this, you can prove actually that all of these lines, the extensions of the reflected light rays, they all intersect at the same point, at a single point in space. So what that means is that if you were an observer, and this is your eye over here looking at the mirror, well, your eye is going to catch light rays reflected from the surface of the mirror, but notice that all of those light rays seem to be coming from the same location behind the mirror. They seem to be coming from a common point. So what we say that, or what you're going to see then, is that there is a copy of the object located in front of the mirror that looks to be behind the mirror. There seems to be an object placed behind the mirror that is producing light rays, which are the light rays that that your eye is capturing and focusing on. And this sort of copy of the object is what we're going to call the image of the object. The object is in front of the mirror, its image is behind the mirror. It looks as if there was an object behind the mirror. That's what we call the image of the object. As I said, using those angles in front and behind the mirror that are the same, you can prove easily that the distance to the object, that is the distance between the object and the front of the mirror, is equal to the distance between the image and the front of the mirror. These two distances are actually equal to each other. This is the case for a flat mirror. The image of the object is at the same distance as the distance to the object. This is a picture that I took many years ago took a picture of Crater Lake, and you can see that a cloud, the distance to the object, in this case the cloud, is equal to the distance to the image. So again, this is the case because of the law of reflection that says that the angle of incidence is equal to the angle of reflection, and that gives us a consequence of that. We get that the distance to the object is equal to the distance to the image in the case of a flat mirror. Alright, I'm going to leave it there. In the next video, we're going to discuss refraction.